Hi there, this is Jacob Nash, and in this video we'll be talking about the fundamental theorem of calculus, part one. So, you know how different things that we've learned in math are inverse operations of each other. So, addition, subtraction, things like that, right? You might be wondering at this point, are we able to say that about derivatives and integrals? We are, but it's not so simple because there's a lot of things that have to go into effect. So, how are we able to say this? So let's just say that capital F of X is the antiderivative. So uh, the antiderivative of a function that is lowercase f of x. And if we're going to say that um, we have something like this, and I'll explain what it means in a second. How are we able to say that when we do this, that we get f of x? Or in other words, we take the derivative of the antiderivative. How do we know that we're going to get back to the original function? So there's a few things that have to go into play. So whatever interval that we're talking about has to be continuous. And if you see here, you might be thinking, well, what's going on here? We have it. Our interval is a to x. Well, really our interval is a to b. But the reason why we say a to x, we're just saying it's not the whole interval. It's just part of it until we get to a certain value, um, x. But a is, I'm using a, but it could be any number. It could be 1, 6. But x, we're almost considering, remember, we're doing, this means an area under a curve. And we're almost considering it a function. And I won't talk about that. You don't have to understand that right now. But that's in case you're wondering why it's like that. Then you might also be confused about why we also have two t's here. Once again, it's too complicated for me to talk about right now, because that's definitely in higher level math. But whenever we are using this FTC, we have to have something that's called a dummy variable, which might sound kind of weird, but it just means any variable that's not the same as whatever is here. And in this case, it's t, but it doesn't have to be. It could be x as long as the other thing wasn't x. As long as they're two different things, but it's called the dummy variable. And uh, so we have to know that the interval a to b, with x in the middle of it, is continuous and differentiable. And we have to assume that this is true. Um, but this only works if there's three things. So here's the three things that you'll need to know, and then we'll look at some problems. So we have to look at the dummy variable and see if it matches. So you see how there's a f of t here and a dt. Remember, the integral always has this thing right here and this thing, and this is the thing that we are integrating. And the variables have to match for it to work. So the dummy variables have to be the same. So it's two t's right there, so that works. Then the thing that is right here has to be the variable, and it has to be by itself. So to make it make a little bit more sense, I'll just replace a with 2 as an example. The 2 could not be here. It has to be the x, and the x has to be by itself. It couldn't be 2 plus x or x squared. And we are going to see what to do if that's not the case, like if the x is on the bottom or if it's not by itself, because you're still able to do something. And then another thing is this has to match this. So that's the last the third thing. So the first thing was these two things have to match. They're both t's. This has to be an x by itself. And then these two things have to have the same variable, which is x. And from that, what we are able to say is that f prime of x, or the capital F prime of x equals lowercase f of x. So we're saying the derivative of the antiderivative undoes itself, and we get the original function, which is the same as like how you can do something like this, and then it's just x, technically negative and positive, but we're just going to say that. We're just saying that this is almost just a statement saying these two operations undo each other. And we're able to say it because of the three things I talked about. Now let's look at an example where it's not just, vague. Let's actually put something in there. So let's do this. So we're saying the antiderivative, whenever I put a capital F of x, that's what I'm saying, but it's possible someone could use g of x or something. Just read what the question says. Um, but we're saying this. And we want to know what happens if we take the derivative of this. That's what prime means. And what is this saying? This means this statement is saying we're integrating 1 plus t. The answer is going to be this. Now, why? Here's why. It's because we have two dummy variables that are the same. We have x here, it's by itself. And then we have this x here, and it matches this x here. And I kind of skipped a step, but we would do ddx for this, and that matches. And so just keep in mind, you always have to make sure it's x now, it's not t, but we just take this thing and then put it there, and then we use x. Now, if I were to change this to a 1 or an 11 or 112, the answer would actually still be the same. It doesn't matter what this number is here, just to let you know. And the reason why is because when you do this in a more complex way, things cancel out, because if you remember, if you take the derivative, you end up taking the derivative of 112, and then since that's just a number, it ends up going away. So this is the reason that's how it ends up. So that's pretty easy, right? Now let's look at a different example. Right? Well, let's say we have this instead. What if we want to find f prime of x? Well, even though this might look more complicated, it's actually just the same thing. We are able to say this. And look what I did. I just took that middle thing and I just replaced it with x. And the reason why I can do that are three things. We have two t's here, our dummy variable. We have that x that's by itself. And then when I took the derivative of this, since we're trying to find f prime of x, we are doing ddx, and that matches. And I replace it with an x. Now, the thing that you have to say, like some of these theorems, is we have to say, I should have mentioned this before, but we have to say by fundamental theorem of calculus part 1, that's how we're able to say this. All right, let's look at an example where those three things don't work out. Now, remember, the first one is, are the dummy variables the same? if they're ever not the same, that's not something that we even do in Calculus 1. That's not what we can do. So you don't have to worry about that. You have to know that it's one of the things that have to be true, but it always will be. But the thing that won't be true is that sometimes the high number or the end of the interval might not just be x. It could be a number or something attached to it. So let's look at an example here. Let's say instead, oh, we have something a little bit different. What if we had h of theta, and then we have this? Well, this time it's not so easy. And let's go through our three things. We have the two dummy variables that match up. Sorry about that. I didn't realize. Wasn't scrolled. Um, but then the next thing is this top number our variable? And it doesn't have to be x, by the way. It could be, like I said, it could be anything. Is it theta? No. So that means that we're going to have to flip those around because at least it is down here. It's not that hard because you might remember that we have a rule that we can do that, and all you have to do is just make it negative, and then you are able to flip it. Um, so now we have theta up here and 6 down here, and then the thing that's in the middle does not have to flip. That's something important. You just keep that part the same. And now, by fundamental theorem of calculus, part 1, we are able to say that h, let me just use a different color, h prime of theta equals negative, and we just put the same thing and then we just replace t with theta. So that's pretty easy. What is harder is when obviously in the example so far, theta and x have been by themselves, but if they're not, then it's not as easy. You have to do something else. So let's look at an example like that. Um, uh, okay. Let's say, what if we had this? We're trying to do this. Okay, so this isn't going to work out this time. Our dummy variable is the same. That's good. The x is on the top, but it's not by itself. It has to be x. It's x to the fourth. So if you remember something that we did earlier in the class, you can do this sort of thing. It's not called substitution because we are going to learn actual substitution, but this is a method where essentially what we're doing is we're to kind of clean up our work. We're just going to replace something that's long with just a simple letter. And commonly what people use is u. Sometimes you might use theta, but I'm just going to use u. So we're going to say u equals x to the fourth. Um, Now we have this ddx right here. We're going to have to know what ddx of u is. So if we have ddx u, that's just u prime. So we have u prime, and that's just a derivative of x to the fourth. And now what do we do? Well, we have to replace the x to the fourth with u, and we'll see what happens if we do that. All right. Well, now we have a different problem. And that is, I said that these two things always have to be the same, and they're not. We have to make it ddu instead of ddx. And there's an easy way to do this. All we have to do is uh, something that seems a little bit strange until you get used to it. So we have to think about, all right, how can we get to ddu from ddx? Well, here's how you do it. We're going to say, okay, we'll just separate the numerator and denominator. So we'll have d and dx. We're multiplying two fractions. It's not really fractions, but we put du's there. This statement is true. These are equivalent because these du's would cancel out and we would end up with dx again. So what we do is we put this part here and then we put that part on the other side. We're able to do that. And by the way, du dx is our u prime. So now we'll just rewrite this. We'll put the ddu on the side, like that's the point of what we were trying to do. And now it matches up. Sec x dt. Now there's one more step. We have to put u